Okay, today's video is entitled Part 2 of RL circuits. R because we have a resistor and L because we have an inductor. And in this video, I'm going to be summarizing what we saw in the previous video where we did a simulation where we talked about how the voltage and the current change over time when we're charging and discharging the inductor. If you'd like to link to the first video, you can do that up in the upper right-hand corner of this video. And what we're going to do is we're going to talk about charging and discharging the RL circuit. We're going to charge the circuit through this branch where we have a 10 ohm resistor, a 12 Henry inductor, and a 25 volt battery. And then we're going to discharge the energy that's stored in the magnetic field inside that inductor through this 10 ohm resistor, which in the previous video was a light bulb. Okay, now we know that at any point in time when we're charging, that the voltage across the resistor plus the voltage across the inductor has to be equal to the voltage of the battery. We can rewrite that as the voltage of the battery is equal to IR because V equals I times R is Ohm's law. And we calculate the voltage across the inductor as L, the inductance of the inductor, times the rate of change of the current. Now what we did to charge this inductor was we closed the switch. When we closed that switch, we saw that the current through the circuit when we first closed the switch is 0. That means if the current is 0, that means the voltage across the resistor is going to also be equal to 0. Well, where is all the voltage? Because we closed the switch, no voltage here, 25 volt battery. All of the voltage, therefore, is going to be across the inductor because that's when we have the greatest rate of change of the current. So when the switch is first closed, the voltage here is 0 and the voltage here is 25 volts. Well, over time, yes, the current is increasing, but the rate of change of the current is decreasing. That means that this term is decreasing to 0 and that the current through the resistor is increasing. So then after a long time, after the rate of change is 0 and we reach a steady state through this inductor as we saw, then this term is 0 and there's no more voltage across the inductor and all the voltage is across the resistor because the current has reached its maximum, which in this case was 2.5 amperes. Ohm's law, V equals I times R. The current in the circuit is the voltage divided by the resistance, which is 2.5 amperes. So then we had reached our steady current through this branch of 2.5 amperes. And then what we did was we closed this switch and opened this switch, and then the energy that was stored in the magnetic field of that inductor was discharged through this 10 ohm resistor. And at the beginning, when we first closed the switch, or actually when we first opened this switch, the maximum current we said was 2.5 amperes, the voltage of the battery divided by the resistance. And then as that light bulb, as that resistor uses up that energy to create light and heat, then the current through this branch goes back to 0. Okay? And we saw that, and we'll look at those graphs in just a moment. We can summarize that kind of in this table here for charging the inductor. This column is when we first close the switch at time equals 0. And this column is kind of at time equals infinity, or we just say after a long time. When we first close the switch, there's no current in the circuit, so the current is equal to 0 amperes. And from Ohm's law, V equals I times R, if the current is 0, then the voltage across the resistor is 0. And we said, well, if there's no voltage here, then all the voltage has to be across the inductor, so the voltage across the inductor is equal to the voltage of the battery. Then, after a long time, we reach our maximum current. And now, all the current is flowing through, or we reach our maximum current, we said is 2.5 amperes. Therefore, we have a maximum current, and again, Ohm's law, V equals I times R. Now, the voltage across the resistor is equal to the voltage of the battery, and all the voltage is here, and the current isn't changing anymore, and the voltage across across the inductor is dependent upon the rate of change of the current. The current's not changing anymore, and now the voltage across the inductor is going to be equal to 0 volts. Okay? So it kind of switches from all the voltage across the inductor and no voltage across the resistor. And then after a long time, we have all the voltage across the resistor and no voltage across the inductor. And we can see that in these graphs. This is the graphs of the charging the inductor, current, voltage resistor, and voltage inductor. You can see we have this curve. It's not a straight line. It's not a steady increase. But you can see the current through the circuit increases over time. V equals I times R. Therefore, the voltage increases. These two curves have the same shape. And then you can see the voltage across the inductor goes to its maximum at 25 volts. for this case, and then decays back to 0, okay, over time. Okay, and then when we discharge, for the discharging, we had our maximum current, which we said is 2.5 amperes. We got that I max is equal to the voltage of the battery divided by the resistance, which was 2.5. And then as we discharge the energy, the current through the circuit goes back to 0. And when we first opened the switch to discharge the energy, we got a maximum voltage, which was equal to the voltage of the battery. The voltage across the resistor goes back to its maximum. But then, as the energy is used by the resistor, the voltage across the inductor goes back to 0. Okay, so these two curves are both decreasing the current and the voltage across the inductor. All right, so I think that's all I want to do. I just want to do a quick summary of what we saw in the first video, which again you can link to in the upper right hand corner. I just wanted to go over the discharging and the charging cycles for that inductor in an RL circuit, and that was the current and the voltages in that circuit. Okay, so thank you very much. I hope you found the video helpful. If you did, please do all the following 3 things. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Leave me a thumbs up for this video and leave me a nice positive comment in the comment section below. Thank you very much for watching. We'll see you in the next video.